Hey, welcome to another edition of Math That Matters. Today we're going to look at AM4, Awesome Math 4, where we're just kind of considering all of these beautiful things about mathematics and how they're interrelated, connected, and we're finally ending the semester with the culmination of all of the awesomeness, which kind of lands at one of my favorite things in the entire world. So there's like Jesus, my wife's in there, my kids are in there, but somewhere, coffee's for sure in there, but somewhere in the top 5, it's got to be calculus, one of my favorite things in the world. You go through math, you do algebra 1, you do algebra 2, it's kind of the same thing. They're now throwing all of this algebra into geometry, and pretty soon you're just rolling your eyes. You get to pre-calculus, it's basically algebra 2 again with some trig, and then you get to calculus, and suddenly it's something new. Suddenly it's something magical. It's incredible. And even though I know there's some high-level algebra within calculus that is beyond the scope of this course, there's some ideas in calculus that relate to the infinite that we're going to explore and you're going to love. So let me share my screen with you. And I made a little PowerPoint. We're going to be doing some problems together too, so this will be a lot of fun. Let's see what we got. Yeah. Okay, so yes, to infinity and beyond. Of course, calculus is the quantification of the infinity. So what in the world does that mean? That somehow we're taking the infinite, the never ending, and we're trying to put it into a container. We're trying to understand and put a number to something that has no end. And we can talk about not just the infinitely large, we can talk about the infinitely small, we could talk about the infinitely fast, and calculus can just handle it. So it's all about putting some things into containers that didn't seem to be able to be contained and then making use of it. No one will ever say that knows calculus, hey, where will we use this? Because it's everywhere. This is called Take It to the Limit, Part 2. Neil's tag teaming me, and he's been talking about the golden ratio. He's been talking about the never-ending spiral. He's been talking about the idea of a limit, and I want to talk about the idea of a limit with a little bit more formality today. So take it to the limit, and of course, you probably know the old Eagles song, Take It to the Limit. So put me on a highway and show me a sign. Take it to the limit one more time. Of course, who can't hear that in the back of their mind? But you can't because you're young and we are old, but Neil's going to love that part. So there you go, Neil. From the Eagles, Take It to the Limit. Here, I'm about to put them on a highway and show them a sign to the better life of calculus. To start things, and I just love this, this never even crossed my mind really until just a few days ago when Neil was teaching. I was thinking about the infinite put into some sort of different container that can contain it. And I thought about the incarnation, that God set aside, as it says in Philippians, the fullness of himself in some way, and took on the flesh, took on the form of a man. He who is infinite made himself finite and contained himself. Though he is ever present as God, he contained himself in the presence of a child who grew into a man, which is just crazy and cool and awesome. So I love that. And that's what we're trying to do. Maybe everything that we try to do in mathematics, whereby we can actually find a container for the infinite, which is again what calculus is all about, maybe that is just a sign pointing to the highway toward God, that we would, as John the Baptist said, fill in the low spaces, and we would level the high spaces and make a path for the coming of the Lord. So I love that. And it's funny, it dawned on me, it just struck me as profound when we were looking at 0.333333 repeating forever, 0.3333 repeating, and I just thought, we can contain that. Even though it goes on forever, if you just want to go to the right, if you want to hold it in a decimal, you can't contain it. It goes on forever and ever and ever, but you can hold this into a fraction as 1/3, and it fully embraces and absorbs all those threes after the decimal. I love that. So maybe you remember how to do that. And as promised, I'm actually going to prove that 0.9 repeating is 1, which might just blow your mind. 0.9 repeating does equal 1. We actually, in the in-person class, we voted on this, and I think a whole bunch of people voted maybe against me. And if you don't ever stop and you have 0.9999999, you get to 1. Mr. Rigsby, my 7th grade math teacher, taught me how to prove this. And I mostly just remember that. And I also remember Kelly. Kelly was this redhead in class, and she was in 8th grade. I was in 7th grade. Kelly kind of like Rob. But I was just kind of enthralled with Kelly, I guess, until I learned how to prove that 0.9 repeating was 1. But, you know, such is life, right? So let's see. If you have 0.9, so this is just a scale that goes up to 1, and then there's a line at 1. So if you have 0.9, you clearly do not have 1. But if you do 0.99, that's real close to 1. And if you do 0.999, that's real close to 1. And so this is sort of trying to show you what's called convergence. So if you stop somewhere when you do 0.9 repeating, if you decide to stop, you know, after 4 nines, you're really, really close to 1. But the question is, do you actually get there? 0.9 repeating, is that exactly 1? And it is. I saw this online. It said surreal 0.999 is not equal to 1. That actually is a lie, and we're going to prove that that's a lie. So I'm going to run over to my trusty whiteboard here. You can, I'll stop this slideshow so that I can, do I have to pin myself so that you can see this? No, I can just stop the share. There it is. There it is. Yeah, so let's just do this. Let's just write the number 0.999. Let's just let it repeat and go on forever. And what I'm going to do is I'm just going to call that x. So x would be 0.9 repeating. And now I'm going to, this is an equation. If I can find x, then I know the answer, right? X is 0.999 repeating, but I'd like to write x a different way. So I'm actually going to take both sides of this equation, multiply by 10. So if I multiply the left side by 10, I get 10x. Now notice if I multiply 0.99999 by 10, I get 9.9999 repeating like that. So I actually have 2 equations right now. And then I just want to subtract them. So I'm going to take the second equation away from the first. So 10x take away x would actually be 9x. It's pretty easy. And the cool thing about this right side, it does what we call telescoping. So we actually have 9.99999 minus 0.99999, which clearly is 9, right? And you see what's happening here. Now, if you divide both sides by 9, you can solve for x, and x, of course, equals 9 over 9, which is 1. So that's definitely worth a boom. Pretty exciting. Look at that. You thought something was just like impossible. How can we do it? And there's this little technique taught to me in 7th grade by Mr. Rigsby. So there it is. Proof beyond the shadow of a reasonable doubt. Fermat, the famous mathematician from France, said a good proof compels belief. So hopefully you've seen this, and what you doubted before, suddenly your eyes were open. It was like you were blind and now you see. It's a simple little procedure, but we've learned how to create a container for 0.999, and actually that container is 1. We could easily create the container for 1/3, and you know, we could say x equals 0.33333. We could multiply by 10, and we'd say 10x equals 3.33333. Subtract them, and we get 9x equals 3, and then we divide by 9. 3 over 9 is 1/3. So a really cool thing, compels belief. That means you saw it, you didn't believe before, but now you have no choice. You say, even if I didn't want to, I do. I do believe. Help me overcome my unbelief. Good times. Well, let's keep talking about this idea. This is great stuff. You may recall from days gone by that Neil was talking about how he had gotten a speeding ticket. And so I was just thinking, should Neil actually have gotten that speeding ticket or not? Because in class, he was saying, I don't think that's fair because speed is just distance over time. And if you take distance over time, it's always an average. So if the cop said, I'm giving you a ticket for how fast you were going, essentially the cop would have had to say you were going an average speed. And he said, my average speed isn't necessarily the speed right now. So he was making the case that he shouldn't have gotten a speeding ticket. Well, I was looking for this picture of Neil as a cartoon online, and I found this website, which actually I should go and show you this, because sometimes you look at something online and even though it's not totally related, it's interesting. So 9 unexpected speeding ticket facts. I won't go through all 9 of them, but I was just like, that's really interesting. The first ever speeding ticket was for going too slow. Come on, that's cool. Not really a part of this lesson, but the world speeding record is recent and huge. Look at this Lamborghini. This guy's driving it, a 25-year-old in Dubai, racked up 33 speeding violations to the tune of $45,000 in speeding tickets. I suppose if you've got the money for a Lamborghini, maybe you've got the money to pay those tickets. I've always thought that wasn't real fair, that if you had a lot of money that you could drive as fast as you want. Kind of crazy. Some other really interesting things. Lots and lots of speeding tickets in the world, and we have some data on that. Speeding is actually dangerous. Come on. We kind of know that. Speeding is big money loss. See, you can totally go down a rabbit trail and start learning things that you never thought you cared to learn. Police officers apparently do give tickets to raise money for their town. We always kind of knew that. Just stuff, right? So probably that was just a little divergence from the actual lesson, but I'm going to give you a chance in the homework to decide after you listen to my compelling proofs to decide if Neil deserves a ticket or not, because we don't want Neil to waste his time and go to court and try to make a case if he shouldn't. So we'll let you decide on that. So what do we want to do with all this? We want to know one of the 2 questions today that is fundamental to calculus. There's only 2 questions in calculus. One is how fast, that's what we're going to look at today. And the other is how much, like how much has accumulated if we knew how fast it was, say, like coming down, like snow. If we knew how fast snow was coming down, even if it wasn't coming down at the same rate all the time, we should be able to figure out how much accumulates because we can see it on the ground, right? But today we're going to focus on the how fast right now question. How fast, we call it instantaneous velocity or rate of change at a point. Sometimes they use that terminology. Sometimes they will call it the slope of the tangent line. But essentially, this is kind of interesting. The notation LIM means the limit. The limit as this little triangle means delta. The limit as delta t. And if you've taken a science class, you know that delta means the change in. The limit as the change in time goes to 0 of the change in s is usually position, the change in position divided by the change in time. Well, if you think about that, that's sort of like miles per hour, but we want the hours or the time element to go down to 0. Well, that's kind of an interesting thought. And then they say equals ds over dt. Well, it's just a slope is what it is. And this stands for delta, which is a triangle over here, and d stands for delta. So ds over dt is really like delta s divided by delta t. And you've seen slopes before as rise over run. So this is a fraction. And the rise is the change in the y's, and the run is the change in the x's. So who cares if we use s and t? So that might be interesting. You remember from Algebra 1, again, that slope is just rise over run. And to find the rise, we find the change in the y variable, which just means subtract the y's to get the rise. You subtract the x's to get the run. Everyone's done this, right? So that's all we're looking for. And the idea is just the steepness of a line, you know, how tipped it is really. So this should be pretty easy, right? Calculus should be pretty easy. And I think I'm going to illustrate it with this problem, the cheeseburger problem. We're dropping it off the Empire State Building, which is 1,304 feet tall. Of course, to make it interesting, into some unsuspecting person's mouth who happens to be lying on the ground. He's hungry. We really want to know, like, is this dangerous? you know, we might want to know, will this cheeseburger fall apart? Of course, it's not going to fall apart because this is a math problem, and everything works perfect in math problems, though not in real life. We'll neglect terminal velocity, which is an interesting question. But we're talking about a cheeseburger falling. There's going to be an impact. Is this going to be dangerous? How will it taste? Of course, it will taste, well, probably bloody, actually. That's morbid. But for our purposes, Superman is on the ground, opening his mouth, and he can handle anything. Now, what we do know here is that the height of the cheeseburger with respect to time is this function. So the 1,304 is the initial height. So we're at 1,304 feet. We drop the cheeseburger, drop straight to the ground. But over time, the height changes, of course, according to this function. So we can look at a graph of time against height, and we can see what's going to happen. In fact, let me just go to my website real quick. If you want to graph that function, this is totally in my way. Leave me alone. I need to get to my stuff. I just went to Desmos, which you can go to Desmos if you want to. Oh, this is really bothering me now. More, how about more? Leave me alone. No, don't end meeting. That'd be bad news. All right, we're just gonna do this. So what I did was I typed this equation. If you go to Desmos, you can type y equals 1,304 minus 16.1, and then I used x. I used x and y instead of height and time. But what you can see over here, and I can even click on these points, is at time 0, the height is 1,304. Click on this point. At time 1 second later, it's at 1,288. At 2 seconds, the height is 1,240. At 3 seconds, it's 1159. All we're doing is plugging in the x to this equation, which I know you can do. You can plug in 5 for x if you want. Plug in 5 for x, you get 902 for y. So actually, you can just plug in all these points. And if you really want to, you can plug in 0 for the height. So if I plugged in 0 for y over here and solve for x, I get 9. It's almost exactly 9. It's kind of cool. So another way to look at this, I actually went to Desmos, and if you know how to deal with parametric equations, I typed in a parametric equation, and I created this straight up and down line, and it didn't matter where I created it at x equals 2, but what we have in these dots is literally where the cheeseburger would be. Initially, 1,304 feet, and then after 1 second, it doesn't say 1 second, but I programmed it so that after 1 second, you can see it's at 1,288. So in that first second, it fell from 1,304 down to 1,288. In that first second, it actually just fell 12 plus 4. It fell 16 feet in that first second, right? And then it went from 1,288 down to 1,240, and then down to 1159. One of the neat things you can see with this illustration is that every second I'm plotting a point, the dots are actually getting further apart, right? Like from this second to this second, that's how far it fell. It fell farther than it did fall the last second. And with each subsequent second, you can see it's falling further. And that's because gravity pulls with an acceleration for you physicists out there, right? It actually is speeding up. The cheeseburger is speeding up. So I thought that was kind of a nice illustration. Well, let's go back to this other graph. And what we're interested in is the speed on impact. So the speed at 9 seconds. So would you agree that the cheeseburger fell 1,304 feet in 9 seconds? I think what I'm going to do is I'm going to take my calculator out, and I'm going to type in 1,304 divided by 9. And actually, that's 1,304 feet divided by 9 seconds. So when I do that, I get 144.88. 144.88 would be feet per second. If you think about that, it's like, well, maybe that's how fast it's falling. But then again, that actually is a slope. It's a rise, and it's negative, right? Because it actually rises down, divided by a run. So if you make a big triangle here, the slope between this point this point down here is 144.9 feet per second. Now that actually isn't the speed on impact. That would be uninteresting. That would mean that algebra and calculus are the same thing. Calculus says, no, you can do better, right? So calculus would say, that's an average speed. How about picking another point? Like, let's say we pick this point right here. At 4 seconds, we were at 1046, and you can see that we fell 1046 feet in the last 5 seconds that it was falling, right? So I'm going to do that. I'm going to do 1046 divided by 5 seconds. Oh, look at that. I actually got, I got 209. 209. What if we got even closer? What if we said, take this point, which just disappeared. That wasn't very nice. How about this point? I've got it. 7 and 515. So 7 seconds, it's at 515 feet off the ground, which means it falls 515 feet in the last 2 seconds. Well, that's a slope, right? I can just do rise over run. I can find the slope between these 2 points. So, oh, it disappeared again. That wasn't very nice. There it is, 7, 515. So 515 feet in the last 2 seconds. That's 257.5. So really the slope between this point right here, 7 seconds and 9 seconds, is 257.5 feet per second. Notice it's actually getting faster. And you can see this last second, it was at 273 feet. So in the last second, from 8 to 9 seconds, it fell 273 feet, which means it was falling on average 273 feet per second. That's a slope between these 2 points. It's going down, so it's a negative slope. But what you can see is the slope actually is getting faster and faster and faster because the average slope is getting closer and closer and closer to 2 points that are close to 9. Well, why couldn't we do this spot, right? Why couldn't we do 8.47 seconds and 148.97? Yeah. Why couldn't we just move this point closer and closer and closer and keep taking a slope? Because everybody knows how to take a slope, right? It's rise over run. You subtract the y's to get the rise, divided by, you subtract the x's to get the run. So that's the idea behind calculus, which is awesome. You just take a point and you just actually take 2 points and you find a slope between those 2 points and you just make them get closer and closer and closer. In fact, you make them get infinitely close together, which seems impossible, but calculus is a new container and it has a tool that allows us, a new container called the limit, allows us to take this slope as these 2 points get infinitely close together, which actually then gives us not the slope between 2 points, but it gives us the slope at a point, which is called the slope of the tangent line. And if you've ever driven your car around a bend at night, what you will notice is when you're driving around the corner, your lights are pointing off the road. So even as you turn the corner, your lights are still pointing off the road. Your lights will be pointing in the direction of the tangent line. And that's what we're after because the slope of the tangent line is the instantaneous rate of change. That's what we want to find. So how are we going to do it? Well, this picture makes a lot of sense to me. It might not make a lot of sense to you. So I'll explain it and then maybe I'll draw it on my board. So this blue function represents any old function, f of x. And then we've got 2 points. We've got one right here, and then we've got another point right here. And if you connect those 2 points, this black straight line is called the secant line. That's just connecting 2 points. That's something you would have done in an algebra class. You might find the slope between those 2 points, rise over run. By the way, look at, they've got a point right here at x, and they've got a point right here at c. So they're just picking 2 points of interest. So you might notice that the y coordinate would be f of x, right? So x comma f of x is a point. And then the y coordinate right here would be f of c. That's just how we write it, right? It just means y when x is c. So can you kind of see that we could just take the slope of that black line, rise over run? rise over run would be, let's see, subtract the y's, you get f of x minus f of c, right? That'd be the rise, f of x minus f of c, divided by the run. Well, that distance would just be x minus c, right? Huh. But then look, they've got this pink line called the tangent line. And what that's really trying to do is that is actually trying to take this point up here and move it infinitely close to this point. So they're trying to get x and c to kind of coincide. And actually you can write that out like this, what this means, and this is the first half of calculus, it's called differential calculus. It's based on what's called a derivative. And a derivative is a slope function, which will tell us the slope exactly at one point. So if I want to find the slope of the tangent line or the slope of the function at x equals c, I just do rise over run, which is f of x minus f of c. That was the rise in the last picture I was showing you. See, look right here. F of x minus f of c. That's just the rise between these 2 points. If I were to draw a triangle like this, divided by the run, but you can see the distance from here to here, that's just x minus c, right? But notice what they do here for this derivative. They put this notation out front. The limit as x approaches c means x is getting infinitely close to c, which is pretty awesome. And the notation for this derivative function is f, the original function, with this little, it's called a prime actually, it looks like an apostrophe. So when you see f primed at c, that actually means the slope of the tangent line or the instantaneous rate of change at some input, some c, which should really help us. So I want you to write this down. You can pause the video if you want to, write that down, and we're going to use that in just a minute on a particular question. In fact, here's the question. We'll just take our favorite function, f of x equals x squared, so this parabola. And we'll be wondering, when x equals 3, what's the slope of the function? So let me just, I went to GeoGebra this time, is another sort of like Desmos. It's an online grapher. And see, I've got y equals x squared graphed here, but I've actually drawn the tangent line here, this red line, and I can move it around. So this is like my car driving at night, and the red line is my headlights. And what's kind of neat about this animation here is you can see the steepness of that red line. It's getting actually less right here, down to where it's flat. So the slope of the tangent line is 0 right there. And then of course it's negative over here, which you can see it's pointed down as you look to the right. But you can also see that we've got a little rise over run kind of thing going on this red line. So the question just asked us, what is the slope of the tangent line when x is 3? And I think if you go here, we get close to 3. There it is. Pretty close. This should be 9, right? 3 squared is 9. But when you get pretty dang close, look at the slope. It's 5.99. So maybe I could get it right there. Yeah, the slope actually ends up being 6, but how do we find that? So take a look at that, and I'm going to erase my whiteboard. I'll show you how to do it by hand. Let's go the long way for finding slopes. And this actually isn't, it's not an approximation anymore, because calculus gives us this limit, which is a container for something infinite. We want these points to get infinitely close so that really we don't have 2 points in a slope. We actually just have 1 point and a slope at a point. So let's stop the share and see what we can do with this. So I'm going to draw, recall, f prime at c, which means the slope of f at some c value equals the limit as x approaches c of f of x minus f of c, which is just rise. We just take the 2 y coordinates. We pretend like there's 2 points. We forget about the limit for a minute. Over, so that's rise over run, x minus c. But then we force x to go to c, which means the 2 points actually converge to 1 point, and we can eliminate the error in the approximation, which is really cool. Now, in this particular problem, we have f of x equals x squared, right? So if we're going to do this calculation, we want to know f prime at c. I'll write this in another color. If we want to know f prime at c, we just write all of this out, but plug stuff into our formula, right? So f prime at c, and I think I said c was 3 in this problem, right, in the slide. So f prime at 3, the slope at 3 equals the limit as x approaches 3 of, let's see, f of x. Well, f of x is just, it's just x squared, right? So instead of writing f of x, I'm going to write what it's equal to, which is x squared, minus f of c. Well, if you think about this, f of c, c is 3, f of 3 is just 3 squared, right? So that's 9. So we got f of x, which is x squared, minus f of 3, 3 squared is 9, all over, let's see, x minus 3, right? X minus 3, c is 3 for this problem. We just want to know the slope at 3. We know it's 6 already. We saw that on the GeoGebra. Well, to take a limit now, we haven't done this, but we've kind of looked at it. To take a limit, what you want to do is you kind of want to plug 3 in for x if you can. So if you can, you just do and you're done. But look at what happens. And this is actually always going to happen in these problems. If we plug in 3 for x, we get 3 minus 3 on the bottom of this fraction, which is 0. Actually, if you plug in 3 for x, you get 3 squared minus 9. You get 0 on top. Means that we've got a hole in this function, and that's no good. So we have to use a little algebra trick here. You might remember this. You might remember that x squared minus 9 factors into x plus 3 times x minus 3. We are doing a little bit of algebra right here. So if I factor x squared minus 9, what you notice is we've got this x minus 3 on the bottom. And what we actually do is we cancel out the x minus 3s, which is pretty cool. And once we cancel out the x minus 3s, what we end up with is the limit as x goes to 3 of, well, all that's left is x plus 3. And now we've got no problem plugging 3 in for x. We just put the 3 in for x right here. We get 3 plus 3, which you can see is 6. 6 is the slope of f at 3. How cool is that? So we just found the exact slope of the tangent line, which is also called the instantaneous rate of change when x is 3. So we saw it in a picture on GeoGebra, and now we found it here. We could plug in anything we want to for x, and we can get any slope on that function that we want. You know, if we would have wanted the slope at 5, for example, all of this would have looked the same, except for instead of 3, I'd have plugged in 5. And I'd have 5 squared, which would be 25. So this would have been 25, right? X squared minus 25. That would factor into x plus 5 times x minus 5. But I'd have an x minus 5 on the bottom to cancel out with the x minus 5 on top. Which is pretty cool. And then I'd add an x plus 5, and I'd plug in my value once I made the cancellation. I could have plugged in the slope at 10 if I wanted to. If I put the slope at 10, I'd add 10 squared, which is 100. So instead of 9, it would be x squared minus 100. But that's just x plus 10 times x minus 10. See, it's going to work out kind of the same way over and over and over, which is pretty good news. Now, that's actually a pretty tedious process when the function gets a little bit more complicated than x squared. And we're not going to get very much more complicated than that. But I am going to show you a shortcut that's really, really cool. So this is the long way for finding slopes, but we aren't approximating anymore. We're finding the exact slope at a point. Now I'll give you the short way. Watch this. And you'll have to do both on your homework, which is fun. By the way, these functions where you see the little apostrophe next to f, these are called derivatives. And when we see that little apostrophe, we use the word prime. So So if you have something that looks like this, and actually I'll use, if I see f primed at c, that means the slope of f. So if you see that little apostrophe, you say to yourself, that means the slope at a point. What point? At whatever x value you put here. So it's the slope of f at point c. F primed at c equals, we're going to want to know what that equals when we have what's called a power function. So let's say f of x equals x squared. And I'll just show you this and I'll show you the formula. The thing that you got to do to find f primed of x, which is just the slope of f at any x value, is if you have x to a power, what you do is you take the power and you pull it in front of x. So I'm going to take that 2 and I'm going to put it in front of x, and then I'm going to write x down, and then I'm going to subtract 1 from the power. So this was 2 and now it's 1. That's all. And x to the 1 is just x. So this is called the derivative of f. I'll show you the formula for it in just a second. And what that means is whatever you want to, you can plug in for x. And if you want the slope of f at that x value, you just double the x value. So f primed at c, well, in fact, we just did f primed at 3, didn't we? F primed at 3. Remember the answer was 6, right? So f primed at some input, which I'm calling 3, is going to be 2 times the input. So that'd just be 2 times 3, which of course is 6. In fact, you can see that with this function right here, all you have to do is double the input to get the slope, which is very cool. Let me show you. I'll prove it to you. In looking at this, right? When x was 3, the slope ended up being 6. Now, wherever I go here, like if x is 2, what's the slope going to be? X is 2, yeah. The slope is it's 4, right? So wherever I'm at, even if I'm at a negative over here, for this particular function, when x is, say, -3, look at this. M, the slope is -6. All you got to do is double the x coordinate on this function, and the slope, you get the slope if you double the x coordinate, which is kind of cool. Now, how do we do that for other functions? Well, if you look at my PowerPoint here, this is the rule. It's called the power rule for derivatives. And it gives you a formula for finding the slope at any x value. So if f of x is x to the n, and this is just for these simple functions, and actually we'll play with this a little bit more because we'll get some other functions that add different power functions to each other, which is called a polynomial. And we can just take the derivatives separately. But all you have to do is you take the power, whatever this n is, like we had x squared, you put it out in front. So we had x to the second, so we put the 2 out in front. We write the x down, and then we just take 1 away from the power. That's all. To create the slope function. And then if you want slopes, you can plug in whatever you want for x. You plug it into f primed, the output of this function will actually be the slope, or the instantaneous rate of change at a point. Yeah, let's actually look at some of these. So you can write those down. I'm going to erase my board, and I'll write them down too, and I'll show you how fast we can find these different slope functions called derivatives. So let's see, we've got 3x squared we've got x to the 4th. We've got 2x squared plus 4x minus 7. And negative 2x cubed minus 3x plus 1. This looks way more complicated than what I just showed you, but it's not. And you'll know how to do it within seconds. It'll be amazing. Okay, I'll stop my share. Look at my board here. I see there's a little bit of a glare, so I'll try to get rid of that. All right, so all you do to find the derivative, which we use f primed for, f primed of x equals, you take the power and you move it out front. Now there's already a 3 out front, but that's okay. I'm going to take the 2 out front, and I just have to do 2 times the 3, which makes 6. And then I write the x down, and then I take 1 away from the power. So the power of 2 will go down to a power of 1. And that's it. Yeah, and I think it said find the slope of the tangent line at x equals 2. So you can always plug in some value for x. So if I write f primed at 2, that just means I do 6 times 2, which is 12. So the slope on the function f at x equals 2 will be 12. This is the slope of the tangent line. How about here? F of x equals x to the 4th. F primed x, that's a slope function. It's a new formula that gives us the slope of f at any x value. And all I have to do is take the 4, put it out in front of the x, write the x down, and then subtract 1 from the power. Then you say, well, how do I find the slope at 2? Just plug in 2 for x. This is a formula. You've built a formula called the slope formula. F primed at 2 would be 4 times 2 to the 3rd. That's 8 times 4. That would be 32. So 32 is the slope of f at x equals 2. Well, how about these down here? Now what we have here is we have a power function and another power function and another power function. And all you have to do is take the derivatives of those power functions separately. So watch this, f primed x equals, let's take the derivative of this. We move the 2 out front. There's already a 2 there. So 2 times 2 is 4x to the first, right? 1 less than 2 is 1. Plus, how about this? This is actually x to the 1. And then 1 times 4 would be 4. And if I really wanted to, I could write x to the 1 less than 1 is actually x to the 0. But I don't really need to write x to the 0. That's just 1. By the way, if you just have a number times x, the derivative, the slope of 4x is basically 4 because 4x is aligned with the slope of 4. So you just write a 4. And how about this? If you want to take the derivative of -7, and if you want to, you can write x to the 0. But if you move the 0 out front, 0 times -7 is 0. X to the who cares because it's just times 0. So if you have a number without any x's, that's a constant function. It's a flat function with a slope of 0. It just goes away when you take a derivative. So here's the answer. If you want to find the slope at any x value, like if I wanted the slope of f at x equals 2, I just do 4 times 2 plus 4. So that's 8 plus 4, that'd be 12. And that's just how steep the slope is at that point. One more, f primed x, we should be able to do this. F primed x is, we're going to do these separately, these power functions. We're going to take these derivatives. 3 times -2, that's -6. X to the 1 less than 3 is 2. Remember, this is x to the 1. You can just remember, if you have -3x, the derivative is just -3. So you don't really need to write x to the 1. But it would be 1 times -3, which is -3, x to the 0, which is 1. And then the derivative of a number is just 0, because that's like 1x to the 0. So you'd multiply the front by 0, and you get 0. So the slope of f at 2 would be -6 times 2 squared minus 3. So this would be 4 times 6 is 24. It's -24 minus 3. So -27 is the slope at 2, which I think isn't too bad. I mean, you're actually doing calculus. We're finding slopes at a point. I'm just going to wrap things up with 2 more thoughts. One is mathematical, and one's going to wrap us back to where we started. But let me share my screen with you. for just a second. So let's go back to the cheeseburger problem. I think we're going to go back to the cheeseburger problem. Yeah, there it is. So we were wondering how fast the cheeseburger was going on impact. So this is exactly the same question that we were doing earlier. You can go back to when we were covering that. Recall, we were simply looking at different slopes between 2 points. So we want to know, like, oh, I guess we dropped 515 feet in the last 2 seconds. Well, I can do 515 divided by 2. That's just rise over run between this point and this point down here. But that's an average rate of change or an average speed. And you could do it from this point to this point. But now we've actually got the ability to calculate the slope at a point. So that's what we're trying to finish up with here. Like if we've got this function, how can we figure out the slope at 9, which is the velocity on impact? So you try it for a second while I'm erasing my board, but we have that function for height, and we want to know the exact slope at 9 seconds. All we have to do is take the derivative of that function. Now, of course, our formula has f and x in it, and this function has h and t, but that shouldn't be bothersome. So I'm going to write h of t equals 1304 minus 16.1 t squared. I'm just writing that on my whiteboard, and then I'll wrap you back to the board here. So what we really want to do is we really want to find, we want h primed at 9 seconds. In other words, the slope of the height at 9 seconds. But we can find h prime now. It's a formula. Pretend like this is f and this is x, right? We're just using h and t. So h primed at t, the slope at t, anytime, the slope at any time, which would be the speed at any time, is the derivative. Well, the first term we have here is just a constant. It's just a number. And the derivative of a constant is 0. If you really want to, you could write 1304 x to the 0. But then the 0 times 1304 will cancel out. So that goes away. And then the second term is negative. We pull the 2 to the front. 2 times negative 16.1, that's negative 32.2. Kind of interesting. That's actually the acceleration of gravity in feet per second squared. Then we've got t as our variable to the 1 less than 2. Oh, that's just 1. So all that means is to find the speed at a particular time, I just plug in that time here and multiply by minus 32.2. That means h primed at 9 seconds would be negative 32.2 times 9 seconds. And when you type that into a calculator, I think I did, it's negative 289.8, negative 289.8. And remember, this is a slope. So the y variable is in feet and the x variable is in seconds. So it's a rise over run. It means we're going down, right? The cheeseburger is going down at 289.8 feet per second. And that is the speed on impact, which I think is really, really cool and awesome. To conclude, I just want to read something to you from one of my favorite authors, Max Lucado. And this will give us bookends of the spiritual significance of being able to put something infinite into a finite container. And again, this is about Jesus being born as a baby. It's called The Arrival. And I'll just end with sort of a thought that way. It all happened in a moment, a most remarkable moment. As moments go, that one appeared no different than any other. But in reality, that particular moment was like none other. For through that segment of time, a spectacular thing occurred. God became a man. The omnipotent in one instant made himself breakable. He who had been spirit became pierceable. He who was larger than the universe became an embryo, and he who sustains the world with a word chose to be dependent upon the nourishment of a young girl. God is a fetus, holiness sleeping in a womb, the creator of life being created. God was given eyebrows, elbows, 2 kidneys, and a spleen. He stretched against the walls and floated in the amniotic fluids of his mother. God had come near. He came not as a flash of light or as an unapproachable conqueror, but as one whose first cries were heard by a peasant girl and a sleepy carpenter. The hands that first held him were unmanicured, calloused, and dirty. For 33 years, he lived on the earth as a human being. At times, he felt weak. There were times where he grew weary. His feet got tired and his head ached. He willingly subjected himself to being susceptible to physical and emotional afflictions. Listen to him. Love your neighbor was spoken by a man whose neighbors tried to kill him. Pray for those who persecute you came from the lips that would soon be asking God to forgive his murderers. I am with you always are the words of a God who in one instant did the impossible to make it all possible for you and me. It happened in a moment, in one moment, a most remarkable moment. The Word became flesh. I can't do better than that. Love you all. We'll see you soon.